Hi, everyone. Oh. Hi, everyone. My name is Olena. I'm working at Matter Labs, and I'm from crypto team. I'm crypto engineer. And today I'm going to present the adventure of zkOS and what does it take to build a multi-interpreter proving system. So let's start from introduction, like agenda. So introduction. Once upon a time, there was an idea of Ethereum shards to have different interpreters. But so far, it didn't happen. So let's fix this. What do you want to see in an ideal blockchain execution environment? So operation system for the next work computers that allows to run and trust and use the program expressed in naive code. Is it a RISC-V ESA? And in our case, in 32-bit extension, and we use default instruction plus extension what includes multiplication and division. Though we assume strictly serial execution model with blocking IPC, and each program will pass resources on itself to the callee. Though it will allow the barrels to build a ZK application without deep learning about advanced math, cryptography, or how to write circuits. So let's look what we actually need for this. So motivation. We know we want one circuit what will manage it by all. So requirements what we need, it's a minimum network complexity, perfectly audited, and to achieve maximum security. As you know, to build the KVM is quite complicated. Every time when you add new feature, like new precompile, it's every time you new audit. And it's kind of long and expensive. And we are not sure that someone won't find a bug because the KVM is actually a big one. So that's why we found a decision. We will have one main circuit, and the zkOS will be proved by one RISC-V circuit instead of many. So it's also, in general, it's much easier to express logic in program code in Rust than in code in Solidity. So the primary advantage of adopting the RISC-V prover lies to ability of significantly simplify the entire system. So unlike this approach streamlines the architecture, making it more efficient. However, for this to be a visible solution, it's critical to a new version operation and exceptionally high speed. So to be better than the KVM, it's supposed to be fast. So actually, the key project has like general name. This is project we can divide by separate small pieces. This is this will be better if I first show. Oh yeah, this. We can divide by ZKE, zkOS, Oracle, and witness generation. But I hide this witness generation inside RISC-V circuits and prover. And let's talk a little bit about how it's interacted with the other and how it's in general work. So let's start from zkOS. zkOS is essentially some interface responsible for I/O. I/O is input and output, and it's responsible for such things like memory allocation, storage, transition storage, and events from arbitrary execution environment. As I expect that it may be memory have been in form like stack or a heap. So zkOS will manage this. Also, I would say that the KOS is kind of abstraction. What's responsibility for resource management? Yeah, and know that we still can implement an all nice trick what we demonstrate by ZK era. For example, lazy storage application, probable pop data discount. whatever we imagine, and all of this can be implemented by one copy of Rust, or another friendly language like C++. And this still can be probable by execution environment. So execution environment of smart contracts that live in its common 32-byte address space follows the same binary interface. And we have 3 of them. It's ERAVM, AVM, and WASM. So, and environments themselves are pure function. They don't need to be in ZK, as I said earlier. So let's detail it. So let's say I give you a couple examples how zkOS interact with zkEE. For example, zkEE want to make a storage write. So here go to zkOS and ask, give me storage slot X for contract Y, instead of contacting the database. So it's like zkOS responsible for writing to storage. Another example of interaction between zkOS and zkEE is receiving like pre-process bytecode, call data, and receive some interface of zkOS program in order that this interface will allow, like I said earlier, interact with storage. Also, or zkOS can do such thing like call new contract, deploy new contract, and self-destruct. So, in general, I would say that zkOS itself is responsible for correctness all this process in some circuit-friendly methods. And for other things, like according to rollup, respectively, it's and also responsible for performing data compression and other rollup-specific things. Also, in another example, interesting kind, if we take a Validium in layer 3, the pub data is not needed. So, but we still need to make storage update for this. And also it's a good benefit that we can easily update modularly zkOS. So let's summarize what actually zkOS do. It's responsible for input-output, bytecode preparation, pull data, memory allocation, booting, process management, memory management, interrupts and execute handling, and all what classic OS have. You also have C, what we have in this. I didn't tell everyone. So I want to emphasize that EE absolutely trivial. So all correctness is guaranteed by zkOS. Correctness from global point of view, so it means like all changes in the storage will be duplicated, and if a set to storage is a minimal, in the fact that minimal like necessary number of modification in the Merkle tree, and things like we call another contracts that we somehow get the bytecode hash in a correct way, and then we decode this bytecode of the hash of the hash, and we guarantee the entire things is also correct. So if you back again, you see the oracle. Let's define what oracle means. So the oracle is some magical thing outside that can put non-deterministic value in the memory, and the system itself should ensure that such value make sense. So also you see in these pictures we have like RISC-V simulator. What is this? The RISC-V simulator simultaneously works with zkOS, and we assume that our RISC-V circuits, what we like, RISC-V like full create for us public input, public output, and we assume that our circuits will prove an execution arbitrary program, and it's our job to define what this program is, and such program is fully covered the logic on conventional block filled with transaction. Also, I want to mention that our zkOS have like 2 modes, forward improving modes. So forward pro mode is when zkOS compiled in x86 and without some of proof machinery, and proving mode is when zkOS compiled to ZK 5 first. So how it works? Step by step. zkOS runs the forward mode in a sequence to process a user transaction first. Later, the witness generator runs a batch again using the forward mode and records the oracle value, like storage. The witness generation then runs inside the RISC-V emulator using the zkOS in the proving mode and builds the witness during that. So let's talk more now about RISC-V circuits and prover, because it's also part of my job, because I'm circuit engineer. And what I said, we have a bunch of optimization. First of simplest ones, I would say, what I implemented, I like put any possible flags, what like identify like, you know that the RISC-V instruction could be like immediate, it could be like register and treat like a theme. And all this flag, actually, we could put maximum as soon as or maximum in lookup, because you know lookup don't need to be like, it's like cheaper than making a constraint. There's another optimization, and interesting will be to say, wait, I have slides for this. Interesting will be to say that we use Emerson field 31. It's order 2 power 31 minus 1. And I think it's perfectly matching with RISC-V extension that we have, 32 bits. And as you know, in small field, it will be cheaper like operation. And what another interesting is we use AR constraint system. Do you know why? Because we're going to use Stark. Stark is better one, because we have like every time the same blocks, and Stark prover is the best for this, I think. So, and interesting, what I see, what's interesting is we use monolith hash for Merkle tree, and we highly optimize optimization of fry. But we also think about change fry to steer. And from another thing, I will think this also will be interesting when we finish all our project, all circuits with all optimization. We have kind of pretty compiler, what a built-a trace. So I think that's all interesting what I can say right now. Thank you for listening to me. And I also wanted to say thank you all people who helping me, supporting me, believe in me. So it's so important to me. Thank you.
Thank you, that's sweet. Any questions for Olena?
Hi, I actually have a lot of questions, but I think I just asked them offline. So let me just ask one question. So you have the zkOS that does so many things, but you're using user mode. As in RISC-V user mode extensions.
Oh, it's not user
so
mode.
So like usually I've seen operating systems that big with supervisor mode.
Yes, we have a couple modes. If you talk about RISC-V, yeah, we have user mode and machine mode. And currently our version work like.
When you say machine mode?
In a user mode, it's not every instruction available, and.
So you are using supervision extensions.
What? In machine mode, we have a whole extension, like basic one, and.
So RISC-V spec is divided into user land and supervisor, and user land. If you just use user land, usually you just target embedded, and when you use both, that's when operating systems come in.
We call a machine mode a supervisor mode, or because, yeah, I think kind of Like supervisor mode is for us. It's easy
Okay.
one.
Okay.
So I mean, like it's not finished yet. It's a row. So we haven't even benchmarked right now. But I think near future we'll have another like deep conversation. Will take more like 1 hour and will be more understandable.
Sure.
Yeah.
And just another quick question. You mentioned that you compile to x86. So this means you're in.
What?
You mentioned that you're compiling RISC-V to x86, right?
Yes.
So you take RISC-V program and compile it to
No,
host.
no. We zkOS compile in x86 for fast, like if we interact like with Oracle and other thing. But we compile in RISC-V for mostly for proving.
Oh, so
proving.
is the source program that's getting compiled to?
Yeah, we have
x86?
two compilation, like for
right.
x86 and second one RISC-V from proving. Like
Okay,
because it's easier.
Yeah, I know.
Proving circuits RISC-V.
Thank you very much.
Thank you. I have one more question here.
Really great presentation. You say you use Marcin 31, but I was wondering if you use an elliptic curve with it?
Elliptic curve? No.
No? Okay.
No. I mean, we use fry commitment, and it's not including curves, elliptic curves.
Okay, so no curves, just the finite field.
Yeah.
Okay, cool.
For fry.
Okay, thank you. Last question.
So I see that the zkOS is supporting MMU, interruption, process memory, and so on, which strongly hints toward, if not parallelism, at least concurrency. But at the same time, you do not support the atomic instruction set. So isn't it a lot of work on a strong impact of performances to implement such complex subsystems if you cannot really use them to their full potential afterwards?
I'm so sorry. I'm a little bad in accent, and I mostly didn't understand the question. But we can talk after. It will be better to understand each other. So.
Thank you. Thank you.
We can talk later.
Thank you, Olena. Great job.
Thank you for listening to me.